If the fire pump controller is in the same room as the main electrical service, mineral insulated, that is MI, cable or other specifically rated cable is generally not required for the controller's wiring. The reasoning behind this is that the fire pump controller is typically considered an integral part of the overall fire pump system, and fire pump systems often have specific exemptions or allowances within electrical codes, such as the National Electrical Code, or NEC. These exemptions recognize the critical nature of fire pump operation during emergencies. The NEC, specifically Article 695, addresses fire pumps and their power sources and control circuits. This article provides detailed requirements for the wiring methods of recurrent protection and disconnect means to ensure the reliable operation of the fire pump. For example, NEC 695.6 details the supply conductors. It says that supply conductors shall directly supply the fire pump equipment. The key here is to understand the scope of Article 695 and how it applies to your specific installation. The exception for MI cable or other rated cables often hinges on the interpretation that the fire pump controller is an essential component of the fire pump system and is therefore subject to the specific rules outlined in Article 695 rather than general wiring requirements applicable to other electrical equipment. NEC 695.6 ATWA says the supply conductors shall have a rating not less than 125% of the sum of the fire pump motor full load current and the pressure maintenance pump motor full load currents. To ensure compliance, a thorough review of the NEC, specifically Article 695, is necessary. Also, consult with the local authority having jurisdiction, or OJ. The AHA can provide clarification on local interpretations and any specific requirements that may be in place. Furthermore, examine the product listings and manufacturer's instructions for the fire pump controller. These documents often provide specific guidance on wiring methods and acceptable cable types. It's important to remember that the goal is to ensure the reliable operation of the fire pump during a fire emergency. Therefore, all wiring and electrical connections must be performed in a workmanlike manner and in accordance with the applicable codes and standards. If the fire pump controller also contains emergency lighting, the emergency lighting circuit is required to comply with the NEC 700 series emergency systems. The size of conductors for fire pump motors is essential for reliable operation. Ensuring adequate conductor size prevents voltage drop and overheating, both of which can compromise the fire pump's ability to deliver the required water pressure during a fire. To determine the appropriate conductor size, start with the motor's nameplate. The nameplate provides critical information such as the motor's full load current, or FLA voltage, and horsepower. The FLA is the most important value for conductor sizing, as it represents the amount of current the motor draws under normal full load conditions. Once you have the FLA, refer to NEC Table 430.248 for single-phase alternating current motors or Table 430.250 for three-phase alternating current motors. These tables list the full load currents for motors of various horsepower ratings and voltages. However, note that the actual FLA in the motor nameplate should always take precedence over the values in these tables. Next, apply the 125% rule. According to NEC 430.22, conductors supplying a single motor must have an ampacity of not less than 125% of the motor's full load current. This is to account for the motor's ability to draw current above its FLA during starting and overload conditions. Multiply the motor's FLA by 1.25 to determine the minimum ampacity required for the conductors. For example, if the motor's FLA is 40 amps, the conductors must have an ampacity of at least 50 amps. After determining the minimum required ampacity, select the appropriate conductor size from NEC Table 310.16. This table lists the allowable ampacities for various conductor sizes and insulation types at different temperature ratings. Choose a conductor size that has an ampacity equal to or greater than the calculated minimum ampacity. Consider the conductor's insulation type and the ambient temperature in the area where the conductors will be installed. Higher ambient temperatures reduce the ampacity of conductors, so you may need to select a larger conductor size to compensate. It's very important to use copper conductors. Copper has a higher ampacity for a given size compared to aluminum, making it a more efficient choice for motor circuits. Copper is also more resistant to corrosion and provides more reliable connections. After selecting the conductor size, verify that the conductor's terminals and connectors are properly rated for the conductor size and material. Use only connectors that are listed and labeled for use with the specific conductor type and size. Use proper torque when tightening the terminals. Improperly tightened terminals can cause loose connections, which can lead to overheating and voltage drop. Another important factor to consider is voltage drop. Excessive voltage drop can reduce the motor's performance and efficiency. To minimize voltage drop, keep the conductor length as short as possible and use a larger conductor size if necessary. Use a voltage drop calculator to estimate the voltage drop for the selected conductor size and length. If the calculated voltage drop exceeds the recommended limit, increase the conductor size until the voltage drop is within acceptable limits. The NEC recommends that the voltage drop should not exceed 5% from the service entrance to the motor. If multiple motors are supplied by the same set of conductors, the conductor size must be increased to accommodate the additional load. Calculate the total full load current of all the motors and apply the 125% rule to the largest motor, and then add the full load currents of the other motors. Select conductor size that has an ampacity equal to or greater than the calculated total. And lastly, document all calculations and conductor selections in the project documentation. This will provide a clear record of the conductor sizing process and will be helpful for future reference. Ensure that all electrical work is performed by qualified and licensed electricians who are familiar with the NEC and local codes. Regular inspection and maintenance of the motor circuits is essential for ensuring long-term reliability. Check the conductor's terminals and connections for signs of overheating, corrosion, or damage. Tighten any loose connections and replace any damaged components. By following these guidelines, you can ensure that the conductors supplying fire pump motors are properly sized and installed. This will help to provide reliable power to the motors, ensuring that they can perform their critical function in the event of a fire. In addition to the motor conductors, the control conductors for the fire pump controller also require careful consideration. The control conductors are used to transmit signals between the fire pump controller and various devices, such as pressure switches, flow switches, and remote alarm panels. The size and type of control conductors will depend on the voltage, current, and distance of the control circuit. For low voltage control circuits, such as 24 volts direct current or 120 volts alternating current, smaller conductors such as 18 American wire gauge or AUG or 16 AWG may be sufficient. However, for longer distances, larger conductors may be required to minimize voltage drop. The control conductor should be installed in a separate conduit from the power conductors to prevent electrical noise and interference. Use shielded cable for control circuits that are susceptible to noise. The control conductors should be clearly labeled to identify their function. Use wire markers or tags to label each conductor at both ends. The control conductors should be properly terminated and secured. Use crimp-on connectors or terminal blocks to ensure a reliable connection. The control conductors should be protected from physical damage. Run the conductors in conduit or raceway to protect them from impact, abrasion, and moisture. The control circuit should be tested to verify proper operation. Use a multimeter to check the voltage and current in the control circuits. The control circuit should be inspected regularly to ensure that they are in good condition. Check the conductors, terminals, and connections for signs of corrosion or damage. Any control circuit or related devices should be listed for the intended use. The selection of the correct overcurrent protection for fire pump circuits is paramount for ensuring both safety and reliability. Overcurrent protection devices, such as fuses and circuit breakers, are designed to protect electrical circuits from excessive current, which can cause overheating, damage to equipment, and even fires. In the context of fire pumps, proper overcurrent protection is particularly critical because the fire pump must operate reliably during a fire emergency. The NEC provides specific requirements for overcurrent protection of fire pump circuits in Article 695. These requirements are designed to ensure that the overcurrent protection devices do not trip unnecessarily during normal fire pump operation while still providing adequate protection against fault currents. The first step in selecting the correct overcurrent protection is to determine the full load current, or FLAW, of the fire pump motor. The FLA is the current that the motor draws under normal full load conditions. This information can be found on the motor's nameplate. Next, apply the NEC requirements for overcurrent protection of fire pump motors. According to NEC 430.52, the overcurrent protection device for a fire pump motor must be sized to allow the motor to start and run without tripping unnecessarily, while still providing protection against short circuits and ground faults. The maximum allowable overcurrent protection is typically 300% of the motor's FLA for inverse timed circuit breakers, and 175% of the motor's FLA for fuses. For example, if the fire pump motor's FLA is 100 amps, the maximum allowable overcurrent protection would be 300 amps for an inverse timed circuit breaker and 175 amps for fuses. When selecting the overcurrent protection device, it is important to consider the motor's starting characteristics. Fire pump motors typically have high inrush currents during starting, which can cause overcurrent protection devices to trip if they are not properly sized. Use inverse timed circuit breakers or time delay fuses, which are designed to withstand the high inrush currents of motors without tripping unnecessarily. Inverse timed circuit breakers have a tripping time that is inversely proportional to the current. This means that they will trip quickly for high currents, but will allow lower currents to flow for a longer period of time. Time delay fuses also have a built-in delay that allows them to withstand high inrush currents. Be sure to check the manufacturer's specifications for the overcurrent protection devices to ensure that they are suitable for use with fire pump motors. Also, be sure to coordinate the overcurrent protection devices with the other components in the fire pump circuit, such as the motor starter and the conductors. The overcurrent protection devices should be sized to protect the conductors from overload in short circuits. The conductors should be sized to carry the motor's FLA plus any additional loads that are connected to the circuit. After selecting the overcurrent protection devices, install them in accordance with the NEC and the manufacturer's instructions. Be sure to use the correct wire size and termination methods. Also, be sure to label the overcurrent protection devices clearly so that they can be easily identified. Test the overcurrent protection devices after installation to verify that they are functioning properly. Use a circuit breaker tester or a fuse puller to test the devices. Inspect the overcurrent protection devices regularly to ensure that they are in good condition. Check for signs of corrosion, damage, or overheating. Replace any devices that are damaged or not functioning properly. Keeping documentation of the overcurrent protection device sizes, types, and settings is essential for future reference and troubleshooting. This documentation should include the motor's FLA, the overcurrent protection device's ampacity, and the date of installation. By following these guidelines, you can ensure that the fire pump circuit is properly protected against overcurrents, which will help to ensure the reliable operation of the fire pump in the event of a fire. In addition to the overcurrent protection requirements, the NEC also has specific requirements for the disconnect means for fire pump circuits. The disconnect means is a switch or circuit breaker that is used to energize the fire pump circuit for maintenance or repair. The disconnect means must be located in a readily accessible location and must be clearly labeled. The disconnect means must be lockable in the open position to prevent accidental re-energization of the circuit. The disconnect means must be rated for the voltage and current of the fire pump circuit. The disconnect means must be suitable for the environment in which it is installed. A discussion about fire pump rooms is warranted. Fire pump rooms must meet certain requirements to ensure that the fire pump can operate reliably during a fire emergency. The fire pump room should be located in a fire-rated enclosure. The fire pump room should be protected from physical damage. Fire pump room should be adequately ventilated to prevent overheating. The fire pump room should be equipped with emergency lighting. The fire pump room should be kept free of obstructions. The fire pump room should be inspected regularly to ensure that it is in good condition. The automatic transfer switch, or ATS, is a critical component of a fire pump system that ensures a continuous power supply to the fire pump in the event of a normal power outage. The ATS automatically transfers the fire pump's power source from the normal power supply to an alternate power supply, such as a generator, when the normal power supply fails. The ATS must be listed for fire pump service. The ATS must be capable of automatically transferring the fire pump's power source within a specified time, typically within 10 seconds. The ATS must be equipped with a manual transfer switch that allows the operator to manually transfer the fire pump's power source. The ATS must be located in a readily accessible location and must be clearly labeled. The ATS must be protected from physical damage. The ATS must be inspected regularly to ensure that it is in good condition. Grounding fire pump systems. Grounding is an essential safety measure that protects people and equipment from electrical shock. Grounding provides a low resistance path for fault currents to flow back to the source, which causes the overcurrent protection device to trip and de-energize the circuit. The fire pump system must be properly grounded in accordance with the NEC. The grounding electrode system must be connected to the building's grounding electrode system. The grounding conductors must be sized in accordance with the NEC. The grounding connections must be made with approved connectors. The grounding system must be inspected regularly to ensure that it is in good condition. Regular testing and maintenance is essential for ensuring the reliable operation of the fire pump system. Fire pump system should be tested regularly in accordance with the manufacturer's recommendations and the applicable codes and standards. The testing should include a visual inspection of the equipment, a test of the fire pump's starting and running performance, and a test of the automatic transfer switch. Any problems that are identified during testing should be corrected immediately. Fire pump system should be maintained in accordance with the manufacturer's recommendations. The maintenance should include lubricating the moving parts, cleaning the equipment, and replacing any worn or damaged parts. A final thought relates to coordination with other systems. The fire pump system should be coordinated with the other fire protection systems in the building, such as the fire alarm system and the sprinkler system. The fire pump system should be designed to operate in conjunction with these other systems to provide comprehensive fire protection strategy. The fire pump system is a critical component of a building's fire protection system. Proper installation, operation, and maintenance of the fire pump system is essential for ensuring the safety of the building's occupants and the protection of property. By following the guidelines and requirements outlined in this summary, you can help to ensure that the fire pump system will operate reliably in the event of a fire emergency. Also note that the absence of specific requirement for a MI cable does not diminish the importance of using appropriate wiring methods that meet the general requirements of the NEC and any local amendments. Always prioritize safety and compliance with applicable codes and standards when installing and maintaining fire pump systems.